Okay, so in this last of sort of what we like to think of as the core foundational lectures for this course, we're going to focus on a discussion of kind of where we are at with deep learning and AI, not only in terms of limitations, but also in terms of some of the most active areas that are rapidly undergoing development and what we can think of as the new frontiers of this very vast field. Before that, I think at this stage in the class, it's helpful to do a little bit of a logistics orientation, and I know we've been receiving a lot of questions around that, so we're going to spend a little bit of time talking about those components first. So as Alexander mentioned, we have this great tradition of these wonderful course t-shirts, so we will start distributing them tomorrow. If you're interested in obtaining one, please come to class tomorrow in person to receive the t-shirts. So far, where we are in the class is we have gone through 5 out of the 6 foundational lectures. And looking forward, we have a series of 4 guest lectures that are going to be from our fantastic industry sponsors, covering a few different topics at the new frontiers of deep learning. Some important deadlines that we're going to get into a little bit more in detail is that for the lab competitions for the software labs, we've extended the deadline from being due tomorrow night at midnight to being due on Friday at 11 a.m. And additionally, there are important deadlines for the submission of the slides to the final proposal competition, also on Friday. And finally, the proposal competition itself will occur on Friday. On that note, as you may know, and hopefully you've gotten practice with, starting with labs 1 and 2, we have 3 amazing software labs for you to gain hands-on familiarity with the concepts that we've been talking about. All the instructions in terms of how to submit the labs are located both on the syllabus and on the actual notebooks themselves for each of these 3 respective labs. So please look to those resources first for those types of questions. For those of you who are MIT students and are taking this course for credit, you have 2 options to fulfill the requirement for receiving credit for the class. Note that submission of the software labs is not required. To get credit, you have to either submit a project proposal and present it on Friday. And here you will be working either individually or in a group of up to 5 people to develop a cool new idea about a deep learning algorithm or application and present it on Friday. And again, all the instructions and details are on the syllabus. Important deadlines, please submit your groups by tomorrow night at midnight, and the slide deck that's linked in the syllabus will be completely locked for editing at 1 p.m. sharp on Friday, so no more editing following that. Importantly, with the proposal competition comes the opportunity to win a few fantastic prizes that are going to be judged by myself, Alexander, our TAs, and a couple of guest judges, including from our industry sponsors. The second option to fulfill credit is to write a 1-page review of a recent scientific paper in deep learning or AI, and this is also due on Friday with instructions on the syllabus. All right, so if you have been enjoying these foundational lectures given by Alexander and I hope that you are ready to really get excited for some amazing new content tomorrow and Friday from our guest lectures from industry sponsors. We're going to have 2 fantastic talks that are going to dive deep into large language models from Peter Grabowski from Google DeepMind and Maxime Lebon from Liquid AI. And then on Thursday, Doug Blank will tell us about the consequences of deploying AI in the wild, what risks, what ethical concerns can come with this. And finally, I will close out by shifting my hat from an instructor mode to sharing some of my own work working at the interface of AI and biology. Furthermore, if you're excited by what you're seeing and you're looking for new resources to extend your knowledge even further, there's an amazing series of resources from my team and group at Microsoft and beyond through the Microsoft Research Forum. And these are some completely public open source talks from our researchers across a variety of areas, everything from the socio-technical implications of AI to how AI is transforming the natural sciences. So please take a moment to capture that QR code and register to receive regular updates about content being distributed on Microsoft Research Forum. All right, so that concludes kind of our logistics whirlwind to kick off this lecture, and now we can really transition to the really fun stuff. So far in this course, Introduction to Deep Learning, we've appreciated not only the foundations of these fantastic algorithms, but also begun to understand how deep learning has truly revolutionized so many different fields and research areas and applications. From advances in autonomous vehicles to breakthroughs in medicine, healthcare, reinforcement learning, generative modeling, robotics, and a whole range of other applications like natural language, finance, security, and beyond. And our goal really here is to share with you a concrete understanding of how deep learning and neural network models have enabled these advances across these ranges of disciplines. And in fact, we've seen algorithms that can not only take as input data in the form of signals, images, other sensory data, and produce a decision out, such as a prediction or a classification, but also how we can do the inverse, right? Going from desired actions that we seek to execute and learning policies that will help us achieve that, like in the context of reinforcement learning, but also new advances in generative modeling that actually tackle this inverse problem directly to be able to train models that can generate brand new data instances. But at its core, in both cases, whether we're going from data to decision or trying to model a distribution of the data itself, neural networks and deep learning can fundamentally be thought of as function approximators. They're really powerful ways to learn this functional mapping or to learn a function that captures a probability distribution. And to understand this concept in a bit more detail, I think it's very helpful to go back to one of the very first and foundational theories in deep learning and neural networks, which was presented in 1989. And this is a theorem known as the universal approximation theorem. And what it states very simply is that a neural network with just a single hidden layer is sufficient to approximate any function within some level of precision or accuracy. Now, in this class, we've been talking a lot about deep models, right, where we stack multiple neural network layers together. But this theorem is ignoring that for the moment and saying, okay, what if we just had one layer? If we believe that a problem can be described as this mapping from inputs to outputs, the universal approximation theorem states that there should exist some neural network to solve that problem. Taking a step back, right, this seems like a very powerful result. But if you look more closely, there are a couple of caveats that we have to consider. First, this theorem makes no guarantees on the number of units, the number of neurons within that layer that would be needed to solve such a problem. And it doesn't provide any methodology or guarantees on how you can actually go about learning the weights, right, that would actually support such a neural network architecture. It just claims this and proves that one exists. But right, as we saw back in lecture 1, this process of gradient descent can actually be very, very complicated. And so it's a highly non-trivial problem to actually do this optimization. What I think this theorem can start to speak to is an example of how we can counterbalance our considerations of not only the strengths of deep learning and neural networks, but also the hype in these fields and the potential limitations that could arise. And together as a collective community and as individuals in this course and beyond, I think we always need to be cognizant of not only the power of any technology, but the limitations that come with it as we go out and use them in the real world. And so in the first part of this class, we're going to talk and touch upon some of the important limitations of these algorithms that you've learned about. One of my very favorite examples of this concept comes from this now classic paper that is entitled Understanding Deep Neural Networks Requires Rethinking Generalization. And in this paper, they do a really elegant experiment. They take images from a data set, ImageNet, and their labels that you see here. And what they do is for every image in this data set, not considering classes, but individual images, they flip a k-sided die, right, where k corresponds to the total number of classes that are possible. And basically, based on the result of that random sample, they now assign a brand new label to each individual image. What this means, right, is that these new labels are associated with no semantic meaning relative to the image. And what you may be able to observe here is that you could have two instances of the same class that are actually now assigned different labels, right? So this mapping is completely random. We're literally trying to randomize our labels entirely. Now, with this randomly labeled training set, what they did was they trained a deep neural network model to this sampled data, ranging from the untouched data on the far left of this plot to completely randomly assigned class labels on the right. And now, when they do the classic test of measuring performance on your testing set, as you expect, the accuracy of the classification really progressively decreases as the degree of randomness in this labeling increases. But what was really striking was what they saw when they now looked at the performance on the training set. This is what they found. No matter how much they randomize the labels, the model is able to get close to 100% accuracy on the training set. And this really points to this idea of relating back to the universal approximation theorem and thinking about neural networks as function approximators. A neural net can perfectly fit to a function, even if that function has entirely random labels. And this gets at, again, that core principle of what is this notion of fit and how you can actually measure generalization and the fit of your model on test versus trained data. And so to drive this point home even further, if we're operating with this framing of understanding neural nets as function approximators, what the universal approximation theorem tells us is that they're just really, really good at doing this task, where given some training set data, we can learn a maximum likelihood estimate of that data, fit a function to that data, such that if we give the model a new data point, say here in purple, we can use our neural network to predict the likelihood estimate for that data point. But what if now we extend the spread of the data further out of distribution relative to these training examples? What happens to the behavior? There are no guarantees on what the training data looks like in these ranges. And this notion of generalization is one of the huge limitations that exists. And further, if we look here at these places that are out of distribution where the model was not trained on enough data, it gets at this question of how do we actually know what our network does not know? And when we consider these examples or use cases, how can we calibrate our expectations of the confidence of the neural network with its actual performance ability? And I think this really points to sort of kind of this magic and excitement about deep learning and AI. And there can also sometimes be a misconception that deep learning is basically this intuitive art, this alchemy, akin to alchemy, right? Where maybe you have some problem and task that you're interested in solving, and you have some data set associated with that task. What if I just build or deploy some AI solution or neural network model on that task? while the power is really awesome and we have all this excitement, really it comes down to a couple of considerations. One is, does that task really, is it really suited to be addressed by a deep learning solution? And secondly, what is the quality of the data that you're able to process and curate for that task? Right? Deep learning is not some magic crank where you can put anything into that crank and get a magic solution out, right? There's this famous saying of garbage in, garbage out, and that's really holds true. Your model is only going to be as good as what it sees. And to make this a little bit more concrete, right, this motivates one of the most powerful and pertinent failure modes of neural nets and highlights just kind of how much they depend on the quality of the data they're trained with. So let's use this example where we have images of dogs. And say we want to pass it into an architecture like a CNN, and we want to train the network to now colorize black and white images, go from black and white to color. What could happen here? Let's say we observe this result. And if you look closely, right, there's this pink region at the bottom of the chin of this dog. Why could this be the case?
Maybe dogs usually they like to stick their tongue out whenever it's hot weather. Maybe the data set has a lot of dogs sticking their tongue out.
Yeah, I mean, let's say if we take a look and look at, okay, what are some common ways that dogs pose or, just are naturally in images, we can see that many, many instances of dogs sticking their tongue out could end up in this end result. And I think this really highlights very nicely that these models are building up these internal representations, again, inherently linked to the data that they've seen in training. And this raises this question of now, how do we build robust solutions that are capable to handle instances that they may not have been seen in training? And infamously and very tragically, a couple of years ago, there was a car that was operating autonomously that crashed and resulted in a fatal death of the driver. And it turned out that actually the driver had reported in multiple instances in recent weeks that when passing on that same road, the car would begin to start to curve and swivel towards a barrier that ended up being what it crashed into. And it turned out that actually in the images that the autonomous system had been trained on, it lacked that specific barrier. It was not constructed at the time. So the car had encountered this instance that was effectively out of distribution and resulted in a crash. And this is this core underlying concept of uncertainty in deep learning. And it's failure modes like this that really motivate the need to be able to understand where this notion of uncertainty comes from, to quantify it, and to use that information to actually hopefully make models that are more robust. This is tremendously important in safety-critical applications like autonomy, medicine, facial recognition, security, and privacy, and also in cases in general where we may have imbalances or sparsity or data noise in our data set. Being able to reliably detect and correct for these sources of uncertainty is extremely important. A third failure mode to consider is a very famous one that maybe you have seen previews of. And this is the notion of adversarial examples or adversarial attacks. And the idea here is, again, very elegant and beautiful, which is if we take some data instance, in this case, it's an image of this temple, and we have, let's say, now a CNN, a classifier. And it does a very good job of assigning a high likelihood that this image is that of a temple. Now, the question is, can we apply some small, indistinguishable perturbation to that image that now results in what we call an adversarial example, that in turn leads the CNN model to no longer be able to recognize this image as a temple, assigning a completely different label with very high probability. The core concept behind these adversarial examples is this perturbation, what it's doing and how it is constructed. Remember that when we train neural networks with gradient descent, our task is to shift the weights of the network according to some objective function. And what we're trying to optimize is the set of weights that will minimize the loss dictated by that objective. Really, what we're asking is, how does a small change in the weights decrease our loss? And can we take a step in that direction to decrease the loss? Importantly, what is being changed is the weights for a fixed image input X and a fixed label Y. In adversarial examples or adversarial attacks, the question is kind of flipped. Now the question is, how can we modify an input image or an input instance to now increase the error in the network's prediction? So rather than perturbing the weights to minimize the loss objective, we're trying to learn a perturbation to the input to adversarially affect the decision at the end. And this actually can be realized physically in the real world. So a few years back, a group of students at MIT took this notion of adversarial examples to the 3D physical realm, where they actually used 3D printing to synthesize real-life adversarial examples that would fool a computer vision model. Beyond this, and I think this notion of adversaries is both conceptually very important, but also practically very important. And in turn, these collective themes of the importance of data, uncertainty, point to considerations that we have to have in terms of our responsibility as deployers and developers of AI. And as you may have seen in the software lab for the course, there's also this tremendous notion of algorithmic bias. How could algorithms be perpetuating some of the cultural, societal biases that exist in our world today and are inherently represented in the data that these algorithms are trained on? So certainly this is not an exhaustive list of all the limitations and considerations we have to be mindful of with deep learning and neural networks. But hopefully these notions of bias, uncertainty, get at some of the core considerations that are present. And I think, as technologists and scientists, limitations present the opportunity for development. And I hope that this also serves as a motivation for you all to go out and continue expanding the new frontiers yourself to tackle some of these outstanding questions. So for the remainder of the talk, I'm going to focus on some of the work that's being done with respect to this and introduce a couple of the leading edge new frontiers in AI and deep learning. And as you've seen, right, this notion of extrapolation and generalization is a very, very core principle of deep learning. And today we have seen this notion of foundational and generative models that promise the ability to achieve really robust generalization in a way of being purely data-driven. And I think this is quite exciting and a really compelling way to demonstrate how these capabilities in extrapolation and generalization have been kind of exponentially increased as a result of these foundational models. And so for this talk, the frontier that we're really going to focus on is that of generative models, which we saw in lecture 4, this principle of modeling a data distribution as a way to expand the capabilities of generalization. And so in the first part of the new frontiers portion, we're going to focus a bit further and do a deeper dive on a new class of generative models that have been introduced recently called diffusion models. So if you think back to yesterday's lecture on generative modeling, we discussed two foundational starting points of generative models, VAEs and GANs. And yet, as some of the questions started to raise and we were able to discuss post-class, these models have a few key limitations to be mindful of. First, they can tend to collapse into producing kind of repeated instances of what we call the mean or the mode collapse, meaning like in an example for facial generation of images of faces, you will result in a mode collapse resulting in the model only producing the average face, quote unquote, right? That's very closely linked to difficulty in being able to generate diverse samples and extrapolate out of distribution. And furthermore, these models such as GANs can be very difficult and unstable and inefficient to train. And so these challenges of stability, the quality of the generations, and the novelty of the generations have really led to new methodological advances that have tackled this head on. And one very prominent approach to generative modeling, particularly in the domains of images and video, is this framework called diffusion models. And if you have experimented and played with some of the leading systems for text-to-image generation, the backbone generative model that's driving the image generation is very often a diffusion model. And diffusion models, I think, are really, really exciting because they have a beautiful and intuitive idea behind them that leads to actually quite high quality in terms of the quality of the generations that they're able to produce. So when we learned about VAs and GANs, the approach to sample generation for something like images was what we can think of as a single shot. A VAE or GAN is trying to learn a mapping from some compressed data representation, like a latent space, or a distribution of random noise, in the case of a GAN, to now produce an image or an instance back in that original data space in a single shot. Diffusion models work fundamentally differently because instead of rather than trying to do this in a single shot, they try to generate new samples iteratively by repeatedly removing noise to refine the generative process in this iterative fashion. And what this means is that the learning task is effectively simplified by breaking up into these iterative chunks, such that the end result is that our sample generation quality ends up being much, much better. So let's take a look at how diffusion models work. The core idea behind diffusion models is this notion of a diffusion process, this idea of iteratively adding noise to source data to create training instances, and then training our neural network to learn how to selectively and iteratively undo that noise step by step. So to illustrate how this comes to life, let's use examples of images. Say we have a training data instance like this. In a diffusion model, there's what we call a forward process, a forward noising process, where we take our data instances and progressively and incrementally add random noise to the instance, slowly wiping out the details in that data until we reach an endpoint of pure random noise. Now, these individual instances are separated by just a stepwise addition of noise, right? Then, the task that we actually train the neural network on is to reverse this corruption process, to now go from noise to data instance in this denoising process that such that we can then recover the information in our data back from these noisy instances. To break this down step by step, right, the forward noising process does not require any training. All we do is, given an instance like this image on the left, we sample a pattern of random noise. And we progressively add more and more noise to the image such that we can have these increasing and iterative examples lined up, right, step by step. Then we turn to actually the process that the neural network is trained on and the neural network learns. which is the reverse denoising process. The noising process has given us these time steps of increasingly noisier and noisier instances. Now the task is, given an image or an instance at time step t, can we learn a neural network that can estimate the likely image at the prior time step that has a little bit less noise than what it's seen? So here, we're trying to learn a neural network to do this exact denoising estimation. Given an image at t, how can we arrive at the preceding t minus 1? How can we train such a network on this task? Again, keep in mind that we're trying to compare these pairwise instances that differ by just a step of random noise. Any ideas on how we can actually formulate a loss or an objective to train this model? Yes, the idea is to compare the image in the prior state, and concretely, how can we define this? Let's say we have an image. Yes, how do we define the loss is my question. Yes?
Mean squared error?
Mean squared error, yeah. Something as simple as that, right? It's comparing these two to actually estimate the noise itself. Because the error between these two instances is effectively what the noise is contributing. And it turns out that this is actually leads to a very effective way to train these types of models. Effectively training the neural network to learn these noise differences themselves. Now, that's really the core concept behind how you can train a diffusion model. Once you have trained it, you can then use the trained model for sampling to produce brand new instances. The way that we do that, to sample a brand new generation, is we start with random noise, and then we take our trained neural network, the weights have been updated, that has been trained to predict these residual noise differences. And what it does is it samples new instances of incrementally less noise starting from this initial state. And this process repeats, and as this denoising occurs iteratively, we can see the data start to peek back at us as we repeat this sampling process. Until at the very end, at the final time step of this reverse denoising process, we're back to our original data space, and we have produced a brand new instance in that space. Putting it all together, in training a diffusion model, you're trying to learn a neural network to predict this denoising procedure. And once you have trained, you can sample from the trained model to produce brand new instances. What is very, very powerful now about this approach is that in starting with random noise, we're able to encapsulate a maximum degree of variability. But by comparing these iterative steps, we've deconstructed the learning task into something that's actually efficient and effective to train. We can produce now very high quality and high fidelity samples through a process like this. Diffusion, and these are actual instances that are generated by a diffusion model. And what is really striking is starting that with a completely different instance of random noise yields a very diverse and very different sampled image as the end result. And that's again relating to this concept of how much variability you're able to encapsulate in that start state. And as I alluded to, right, diffusion models are underlying the image generation pipeline for many of these text-to-image models and platforms that you may have seen and experimented with. And I think that this really comes to life through these examples where you can see that the quality and fidelity of these generations is very high with respect to the image itself and how closely it matches the input prompt. It's not just about images or video or things like this that diffusion has become very powerful. In fact, in the natural sciences and in the life sciences, we've seen tremendous advances in diffusion models for molecular design and biological design. And on Friday, I will share a little bit more about how some of these approaches work and the capabilities that we're able to achieve in this application. All right, so that gives us a kind of a foundational understanding of the state-of-the-art generative models for image generation and other modality generation. In the remaining time for this lecture, we're going to go into another new frontier of large language models and give you a strong primer on the fundamental concepts of LLMs in preparation for some of the guest lectures tomorrow, as well as for our brand new software lab that's released today. So I think that it's no secret now at this point that large language models have really taken off in the past years and are truly revolutionizing many aspects of our daily life. But I'm very passionate about not only technology, but understanding the fundamentals of technology that I work with and that I interact with. And so what I hope to convey is a background on how LLMs like GPT, that power ChatGPT, work and why they work the way they do. And with that knowledge, hopefully arms you with an arsenal to understand the capabilities of these models and also their limitations. So very fundamentally, what are LLMs? On day one, we started out by defining, proposing a definition of artificial intelligence and a definition for deep learning. LLMs, or large language models, are very simply very, very large, deep neural networks that are trained on large sets of text data. The way that we can think about this is that these data sets are pretty broad, pretty agnostic, and start out as effectively unannotated. In order to train a large language model like GPT, as we started to get at a little bit, this data set needs to be processed and fed into the model in a particular way. We then have to define a task, right? A learning task and an objective that we want to train the model on. Now, with data of this scale, it does not necessarily, and it's infeasible to fit into a classic supervised learning problem, right? Where for every instance of data, we have some defined label, and our neural network task is to learn a mapping of the data to the label. Instead, what is really the breakthrough and core idea behind these LLMs is to use the data itself to define a task. And a very common task that powers these models, and in fact is what powers GPT, is a very simple one that we saw again on day one. Given a sequence of chunks or words in a sentence, predict the next word, the next chunk. In language modeling, these chunks are often called tokens, and the task is called next token prediction. Given a sequence of tokens, predict the next token. And we're going to update our model parameters, our weights in our neural network, based on how well the model does at this next token prediction task. How does this work? To break it down, and hopefully now these concepts are coming back from the lecture on sequence modeling as well, how LLMs like GPT are trained are by taking raw text in the form of a sentence, for example. And the first step is to split that text up into chunks and represent it numerically through this process called tokenization. Those tokens are embedded, numerically encoded, and provided as input to the LLM. And the next token prediction task is simply as follows. Given a set of tokens, we want to predict what is the most likely next token, estimate the probabilities of what that next token is over the whole vocabulary or whole space of possible tokens. Looking at this very concretely, what we can do is actually compute the probabilities over this distribution of next possible tokens and use the signal from the estimated probabilities to train the model. what is beautiful to realize is this effectively amounts to a classification task. By computing the cross-entropy loss over these next token probabilities compared to the true next token, we are able to provide a signal to the model to learn how to compute this next token prediction task. The beauty here is this is what we call a self-supervised signal. We're using the data itself to define a signal to train the model on. And again, we can employ something very simple like a cross-entropy loss to convey this signal to the model. The power now comes by doing this very intuitive next token prediction task on a very large and broad set of data that allows the model to learn the fundamental patterns that underlie something as complex as human language. Now, when we have trained the model through the next token prediction task, at deployment, you are able to interface in this way where you can prompt the model and now produce responses out. In practice, though, there are several steps in what we call LLM post-training that are actually required to go from that next token prediction task to something that actually functions as a chatbot that you can interface with and interact reasonably with. And in the Liquid AI lecture tomorrow, you will hear from one of the world's experts on LLM post-training the core components of this pipeline and how the considerations that need to be made here. So the capabilities that this unlocks with today's language models are really tremendous in terms of their use as agents for knowledge retrieval, writing, text generation, and so on. And this mastery over language has really been tremendous. Still, there are still key limitations when it comes to the deployment of LLMs and places where they still struggle. First is this notion of uncertainty and confidence that we introduced earlier in this lecture. We still are working very actively on ways to reliably quantify the robustness and confidence of models as large as LLMs in these types of scenarios, such that we can be able to reliably identify what we call hallucinations, where the model may produce a generation that sounds very sensical, but is actually not grounded in reality. And also use this understanding to consider what model-level guardrails we should deploy on these AI systems when they're interfaced with humans and applications. And finally, a fourth and very prominent area of active work in language modeling and these AI models is this notion of logic and long-term planning, such that the models can go beyond this mastery over natural language and generalize to very complex reasoning and planning types of tasks. Nevertheless, a lot of these breakthroughs that we have seen with models like GPT and beyond comes from observations that pointed to the fact that these LLMs can pick up these new emergent abilities as the model size scales and as the data set size scales. And there were some seminal observations in neural scaling laws that pointed out that as we scale the size of these models and how long and the extent to which they're trained, we can see step changes in the capabilities of these models in terms of tasks that they could perform. And really, this concept comes to life very beautifully in this visualization, where you can see very concretely, as a function of the model size in terms of the number of sheer parameters in these models, we see breakthroughs and blossoming of new capabilities that these language models can actually demonstrate and achieve. So these concepts now get quite heavy and serious when we consider the capabilities of foundation modeling and how we are stepping towards closer and closer of what we can think of as true artificial intelligence. And when this course began, we spoke about what it means to be intelligent. the ability to take information, reason about that information, and use it to inform future decision-making. I would argue that our learning pipeline is not restricted to only being able to solve the tasks that we have seen training examples for. Right? We are able to learn concepts behind tasks that allow us to, speed up our ability to learn and generalize and think creatively on new domains or new areas that we care about. As we see these new advances in generative AI, it motivates a deep question for ourselves in terms of what are the connections and distinctions between what we can do, what our capabilities are, and what the capabilities and limitations of these models are. And moreover, like any technology, right, AI is just a technology. We've created it as a technology and as a tool that we can use and we can deploy. And I encourage you all to not only think about the relative similarities and differences between human intelligence and artificial intelligence, but also about how you can maximize these tools as tools for you in your own work and in your own personal journeys of learning and creation. So I'll leave you with that point to think about and meditate on, and I encourage you to discuss further amongst each other. Still, I want to highlight and very excitedly announce that these themes and concepts of LLMs that I just shared, you now have the ability to get hands-on practical experience with actually experimenting with and fine-tuning an LLM yourself. And very excitingly, we've unveiled a brand new software lab. Never before, you all are the first class to have access to this software lab, where you will actually fine-tune an LLM yourself as a chatbot in a couple of different fun styles and try to experiment with it to optimize the performance of your chatbot. And hopefully, you do this. You don't try this. You do this. And this is a preview of what is to come in that software lab. So thank you all for your attention. With that, we'll close, and thank you all so much.